Good morning. We're almost at half capacity. Anybody have any questions before we start? All right, we'll wait about another minute and then we'll get cracking. So today we're going to continue with resonance. I'm going to build in, again, layer in some other topics based on what the videos. I know there's a lot of videos I sent this weekend, and I hope you had a chance to look at them in less than an hour total. But I'm going to layer in some other topics based on what was sent out. So we're going to talk about functional groups as we encounter them. We're going to talk about resonance as we encounter examples where resonance are possible. And then we'll talk about the physical properties and intermolecular forces as we encounter that as well. So, yeah, so we'll do that. So hopefully you took some time out and acquainted yourself with information so that today won't be just cold turkey for you. All right, so let's jump in again. On Friday, we started talking about resonance and how resonance adds stability and how how the more resonance forms you can draw for a molecule, the better. That was also some information that was in the set of resonance videos I sent out about a week ago. And we talked about in order to do resonance, you need a donor and an acceptor, and you need them adjacent to one another, right? So that they can share electrons. All right, so what we're going to do is grab a couple of examples from down here. I'm going to do several. All right, so I'm going to start here. This is a good example of, we're going to start that and then we're going to do the highlighted ones, B, D, and F. So let me put a page in so we'll have room to work. And we're going to get cracking. All right, so I'm going to paste this here. So one of the things that we said about resonance again is that you need a donor and an acceptor. And they must be adjacent. And again, the purpose of resonance is, fix that. The purpose of resonance is to delocalize electrons so that they are not concentrated on one atom. When you can do that, it makes the entire molecule more stable. So over here, it's said to supply arrows to go between these two forms. But, and let me ask this question. Can somebody tell me what functional group this is?
Carbonyl.
It is very good. It's a carbonyl. But what is the specific type? Because remember, carbonyl is generic. So when I have a C double bond O, that's generic until I attach something to it. So if I have a carbon on either side, then that carbonyl becomes a ketone. Very good though. And so you can see here, I got a carbon on this side and a carbon on that side. So this is a ketone. right? So now, can I interchange these two, right? Is there a set of arrows I can put in to interchange them? Let's see. So in this case, let's say that the carbonyl is my acceptor, and then the pi bond is my donor, right? So it's going to be these atoms that are participating. Let me change colors. Sorry. It'll be these atoms that are participating here, 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 right? And then of course the oxygen is a part of that too. But we're looking at the carbon because I'm going to donate a pair of electrons there. So this is a type of allylic system. So it's going to follow a similar rules as the allylic systems follow. So if I take this molecule and I shift this pi bond to here, take these electrons and give them to oxygen, I will not get this resonance form over here. Right? What I will get is this. I can write it right there. Perfect. I'll get this. Sorry. That's negative. This is here. And then this carbon becomes positive. Can y'all see that? Anybody not see what I just did?
Can you redo that?
Which part? The arrows?
Yes.
Yeah, sure. So I'm going to take, remember, my donor can be a pi bond or a lone pair. And my acceptor can also be a pi bond or a cation. So in this case, my donor is a pi bond right here. And my acceptor is the carbonyl. All right. So I'm going to take this pair of electrons, and I'm not going to donate them directly to that carbonyl carbon. I'm going to put them here and turn them into a pi bond. And then if I do that, I have to break the carbon oxygen pi bond because otherwise that carbon is going to have too many bonds to it. So that's what forces the carbon oxygen pi bond to become a pair of electrons on oxygen. So that's what I'm showing here. You can see right here, the pi bond got shifted, right? And then so now I have a resonance, this resonance form.
Is this a part of the homework page too as well? This problem?
I just cut it from the questions up here in 1.36. All right. So let's take another one that's a little bit, well, let's finish this one first. So can I go from here to here? Is that possible?
Yes.
Okay, look at where the pi bond is over here compared to your acceptor. Right? I cannot go from, let's label it, I'll call this A, to form B with any kind of arrows, because it's not going to work. If I move the pi bond to here, just follow the arrows. If I move the pi bond to here, do I have an acceptor down there? Do I have a pi bond or a cation that I'm giving those electrons to?
No.
I don't. Right. So I can't draw this resonance form from A because moving the electrons that direction to make put the pi bond here is impossible. So here we can say that there is no resonance. Right. Let's do another one. Let me pull some of the other problems from up here, and then we're gonna work through them. We'll cut all these off at the same time. because then we can just put the arrows. I just wanted to take that example to show that there are instances where resonance is not possible. Right, so I can't do resonance there. But if I'm looking at, let's say B, right, and let's put the electrons in. So I got electrons here, and then also here. Right now, if you look at B right here, this system is an example of, or it's a type of allylic anion. Right, it's a type. Let me go back and show you, refresh you. So this was the allylic anion right here, right? You see how you have a negatively charged atom, in this case carbon, that's adjacent to a pi system. All right, so anytime you see that pattern, you can do resonance. So let's go back down to here. All right, anytime I see this pattern, I can do resonance. So I'm going to take, how would I put this pi bond here? You see the new pi bond that's formed over here? How would I do that? If I'm doing it through resonance, what I'll do is I'll take a pair of electrons from here and put that arrow right between those two atoms. Notice I did not put the arrow here on carbon, right? Because if I'm working with an allylic anion, the pattern of electron flow is to turn one of those pairs of electrons on the anion into a pi bond, and then take one of the pairs of electrons in the acceptor, which is a pi bond, and turn it into a lone pair. Right? So that's the flow of it never changes. If that's the pattern, that's how the electrons are going to flow. Right? So these two are resonance forms, and it matters where your arrow stops and where it starts. So I start the arrow at the electrons right here, and I stop it between the two atoms because I'm making a pi bond there. Right, you can see that in the resonance form on the other side. And let me see if I can white out some of these little blemishes. I don't want you getting confused thinking those are electrons. All right. Questions about that one?
So if like on the page, it has the two images like you see right there, and it's draw the arrows between both of them. So if you were to go from the figure on the right, would you just do opposite of what you did on the left side?
Yes, great question. So you're saying to go back? Yes.
You would just do the exact opposite.
That's exactly right, because the electrons have to flow in the same path.
Okay.
Yep. They have to flow in the same path to get back to the original form or the original resonance form. That's a great question.
I'm confused on how you know which one, again, is the acceptor and which one is the donor.
Okay, great question. So when you have to choose between, let's say you have both, because we said a acceptor can be a pi bond or a cation, and a donor can be a pi bond or a lone pair. If you have a pi bond and a lone pair present like this allylic system, the lone pair is always going to be the donor, because those electrons are more readily shared than a pair of electrons that are already tied up in a pi bond. If that makes sense.
So is that why the oxygen with the negative or the lone extra lone pair donates?
Yes.
Okay.
That's your donor, and it's connected, it's adjacent to the acceptor, which is a CO pi bond. Are we okay? We following? It's kind of like, I'll say it kind of like this too. Let's say you have a handful of quarters and you're paying for a latte or whatever, and you have a roll of 20s in your pocket. The money that's in your hand is more accessible. So you're going to use that first. You following? Rather than digging down in your pocket, having to peel off money, trying to pay for that latte. So if you have loose electrons or lone pairs, then those are going to be the first to be donated, as opposed to the electrons that make up a pi bond being used as a donor. The other part, which is that's an excellent question. The other part is oxygen is already negative, right? And one of the rules of thumb for organic is you never push electrons towards a negative. You always push electrons away from a negative, because you're trying to stabilize that negative by making it neutral. So here I'm gonna write that in here. All right, so you never push electrons towards a negative charge. You always push them away. So that's another way to think about why I started at oxygen and not at the pi bond. Did that answer your question?
Yes.
Okay, all right, great. All right, let's do the next one. Where's my pattern? If you notice, I'm kind of leading you out, like we at the beach, and I'm just leading you out into the ocean, right? So in the next one, I want you to find the pattern and tell me what pattern it fits. And let me do this. Let me put a little cheat sheet over here so we can have an allylic. I'm gonna write this out. I'm just gonna use carbons. Allylic anion. We can have an allylic cation. There's one other special case, and that's F. We're gonna talk about it when we get to it. Or we can have an allylic radical. All right. So that's our cheat sheet. So which pattern do you think this fits? If you see a negative charge, obviously it's going to not be a cation. Is that right?
Right.
So now we just need to find what? Find the donor, find the acceptor, and push the electrons. So what do you think is going to be my donor here? After that long speech I just gave about lattes and change versus money in your pocket.
The oxygen.
Oxygen.
That's your donor.
Oxygen.
And that makes the pi bond by default the acceptor. That's my donor, that's my acceptor. And I'm going to push electrons here. And I'm going to take that pi bond and put those electrons onto this carbon atom. That's how I get here. And the lone pairs are not shown, but we're going to put them in. Are y'all following? Anybody not see that? So it's these three atoms here and here that are involved in resonance. So and why are they able to talk to each other again? Anybody remember? I think Justin said it on Friday. Why am I?
Because
Go ahead.
they're close enough for the orbitals to overlap.
Close enough for the orbitals to overlap. That's how atoms talk, through orbitals. And that's how they communicate with each other. Not saying that they're human or sentient, but if we want to give it an analogous situation, it's just like, being close enough to talk. So the orbitals are overlapping. Right? Now let me throw in another piece, because we have a functional group here that we can talk about. Anybody? It's not a ketone. It's not an ester. It's not an amide.
Is it a aldehyde?
Come on with your fast. I mean, yes, it's aldehyde. Aldehyde. Very good. Right? You see the difference. Ketone, if this was a ketone, this would be a carbon. But because it's a hydrogen, now the functional group type is an aldehyde. That's excellent. It's an aldehyde. All right. Up here, this is a derivative of lots of different functional groups, but more than likely, the functional group that came from would look like this. Somebody tell me what that is. I'm just going to put an R group over here. What functional group is that?
Is it an acid?
Ooh, man, come on. This is good. Y'all just making my day right now. It is. It's a carboxylic acid. I promise you, if you make flashcards of these functional groups, please do, because you're gonna see this stuff. I spent my whole 9 o'clock class talking about functional groups. This is in part 2. And I shouldn't have to do that because it should already be ingrained. So please, please, please make flashcards. Use the book. The book has a whole 2 pages of functional groups listed. Take that, put it on a flashcard, write the names, and learn them, because functional groups dictate reactivity. Right? That's the rule in organic. Whatever the functional group is going to determine how a molecule reacts. It's going to determine if it likes electrons, or if it likes carbocations, or if it's going to be polarized or non-polar. All of that is dictated by functionality. Right? So please learn those, commit them to memory. That's the only way to learn them, is to memorize them. And the best way to memorize them is by classes. So all your carbonyls fall in the same class. It can be an acid, ester, amide, aldehyde, ketone, so on and so forth. All those are they have the carbonyl group in common, right? And you have other functional groups like ethers and alkyl halides and things like that, which we'll come to later. But you gotta commit those to memory somehow. So make you some flashcards, save them. If you forget one, flip back to it. There's also an app. I think that Organic Reaction app has functional groups in it too, or it may be a functional group app that you can download. But you gotta have them, because this is, again, the reason why we just walking this down is because we're trying to lay the foundation for the hard stuff, so that when you get to the hard stuff, this is not what's tripping you up. All right. It's not plural. All right, let's go to the next one. All right, so this is a special case. This is not a allylic system, right? Allylic system are normally 3 atoms. So the anion, cation, and the radical, which I need to fix, is a 3-atom unit that we can easily spot, right? But in this case, this is a 2-atom unit, and I'm going to put some electrons on oxygen, because otherwise it's not going to make any sense. All right, so look at the form on the right and tell me how we got there. What would you do to put a pi bond between oxygen and carbon, like you see here, that I just highlighted?
Make one of the lone pairs a double bond. Well, into it.
Go ahead.
To make one of those lone pairs on oxygen into a bond.
Yes. So take one of the lone pairs and turn it into a pi bond. This only works if there's an acceptor here, and a carbocation is an acceptor. Is that right? So my donor is here, and then my acceptor is here, right? So I'm going to take that. Look at where my arrow is going. Let me make sure I show this properly. I'm going to make this lone pair into I'm not going to make it disappear. Make it to a pi bond. So I'm putting the arrow between the 2 atoms where I want to put those electrons, right? And that is going to result in a pi bond being formed between carbon and oxygen, right? That's where that pi bond comes from. Notice in the resonance form, the formal charge on oxygen is now +1 and carbon is neutral. That's how resonance stabilizes. Instead of that plus charge just sitting on one atom, if I'm doing resonance between those 2 forms, that means that I'm alternating where that charge is, like constantly. And so that stabilizes. You know, I think in one of the videos I used like a person holding like some kind of load, like bricks or whatever. And the fact that they were able to share that load with another person meant that they were not as burdened. So I'm using that as an analogy. If I have a charge on an atom and I want to delocalize it, the best way to do it is through resonance. So in order to do resonance, I need a donor and an acceptor adjacent to one another. So here's my donor, here's my acceptor, and this is an example of what I like to call just a 2-atom resonance unit. Right? Where you have your donor and acceptor right next door to one another. Now, here's the other question. What functional group is this on the left? What class would it fall into? I just have a carbon with a sigma bond to a hydroxyl group. It's an alcohol. Is that right? All right. That's an example of an alcohol. If I have a carbon, and I know it's a carbocation, but that's beside the point. It's still an alcohol. So I have a carbon that's singly bound, right? And all the other bonds to it are sigma bonds. It's not a carbonyl. If it was a carbonyl, then it would be a carboxylic acid. But the fact that it's just all sigma bonds, then that makes it an alcohol. All right, we're okay so far? Any questions? Ask questions if you have them.
Can you go down to the first set of problems that you did?
Sure. You mean right here or
Yeah, right there. I'm
the
just
top
gonna,
one?
yes, thank you.
Want me to zoom in on it?
No, that's fine. I just took a picture of it. It was kind of confusing when I was trying to write it down.
Okay. If you have questions, just ask. If they pop up after class, shoot me an email.
I had a question back on the first problem, not using dot again.
Okay, go ahead.
So are you not able to transfer the electrons? Is it because it's not adjacent?
Yeah, they're not adjacent, so they can't talk. If you look right here, look at the form that they gave us, and they're asking us to put arrows in to go from A to B. But the fact that in A, the donor is the pi bond and the acceptor is the carbonyl, the only way to push electrons will be the route that I have shown in red. I can't push electrons to this carbon right here, which is what it's asking us to do by drawing this other form. This carbon right here has no way of accepting that pair of electrons. So I can't push electrons that way. I can only push electrons from a donor to an acceptor.
And why can't it accept electrons, the yellow carbon?
Let me ask this question. What are our examples of acceptors? We said pi bond, a pi bond can be an acceptor, right?
A
And a
positive?
cation. Let me just show you what happens if I do that. So let me, this is gonna be sloppy, but let me just draw it, right? And I'm drawing this, I'm gonna draw it, I'm gonna leave all the atoms intact. So if I'm gonna make it in purple though, that might help to keep it orderly. If I drew this, and that's a great question, by the way, because it's good to get that out. This is what it's asking us to make, right? By showing us the form on the right and saying that it's a resonance form, and then giving us the form on the left, which is label A, and telling us to interconvert between the two. If I push the electrons the purple route, I'm gonna write that out here because when I post these notes, you'll hopefully. Right? Look at the carbon at the bottom where I'm pushing electrons, giving electrons to. What's wrong with that carbon?
Oh, and that has 5. Okay, I see.
Yes, good. It's got 5 bonds to it. That'll never happen. And if that carbon is not a cation, or if it doesn't have a pi bond, if it's not, you know, part of a pi bond where I can actually alleviate, you know, how do I put this? Where I can push a pair of electrons away from it at the same time, then this is what I'm going to get. And this is not good because it's not possible. Does that make sense?
Yes.
So I
yes.
have to push them this way, because at least when I push it this way, using that red route that I'm showing, at least when I push them this way, I can alleviate the carbon that's circled in red right here by moving that pi bond to oxygen away from it. Because everything, again, we go back to the octet rule. I have to always keep the octet rule in mind. So my resonance forms have to be legitimate. And B is not a legitimate resonance form from A, because the carbon at the bottom right here will have too many bonds to it, and it will violate the octet rule. All right, is that okay?
Yes.
All right, awesome. All right, let me see, we did all these. Let me find, what are we doing here? B, oh yeah, let's do B, E. Let's cut these out. Because this is a really good exercise right here, because some of these have multiple resonance forms and multiple functional groups. So we're gonna layer those two things together, since, you know, while we can. All right. I'm gonna add another page in because I know we're gonna run out of space. And let's start with, I cut I off. Well, we're not doing I anyway, so it doesn't matter. Which one do you want to start with? You want to start with B, C, doesn't matter.
B.
All right, let's start with B. I'm gonna cut this out because this is one that is gonna have multiple resonance forms. All right. Paste that right there. All right, first let me put some electrons in here. And I'm also gonna put some electrons on oxygen. All right, and that's another important skill to have, because I always put them in like on an exam, but it's just good practice to remember, like Lewis form, how to write a Lewis form, and where to put your lone pairs and things like that. It's very important. Because in a structure like this, without the lone pairs, you may not know where to start. So don't feel like you have to be super advanced and I don't need the lone pair. Always put your lone pairs in, so you keep track of all your electrons. All right. So in this molecule, let's start on the end where the electrons are again, because that's my loose change. I can use those more readily than I can use the electrons in the pi bond. So where am I going to push the electrons first? First thing I need to do is to do what? Identify my donor, or my acceptor and my donor, right? So the carbanion on the end is my donor, right? Making the pi bond my acceptor. And they are adjacent, so they can talk to each other. Is that right?
Yes.
All right. Which way are my electrons going to move?
To the left.
To the left. Good. Towards the acceptor. So I'm going to take that pair of electrons and I'm going to turn it into a pi bond. Boom, right between these two carbons. What about the pi bond? What am I doing with that?
You turn to a lone pair.
Turn into a lone pair on this atom right here. And what am I doing by doing that? I am delocalizing that negative charge off of that CH2 onto another atom. I'm spreading the charge out, I'm sharing the electrons, and I'm stabilizing that molecule in the process. Right, everything comes back to stability. So I'm gonna redraw that. Well, I'll draw what the resonance form is. What functional group is that? Right here, that I just drew.
An aldehyde.
It's an aldehyde, good. Right, so now I have that negative charge on this carbon right here. And can I do resonance again? Do you see the pattern? You see how that carbon is adjacent to a carbonyl, which is a pi system or a pi bond. It contains a pi bond, is that right? So what would you do there? Where are my arrows going? This is my donor. Everybody agree with that? It's got a lone pair. They're free to interact with other atoms as long as they're in adjacent and orbitals can overlap. So that's my donor, that's my acceptor. What are we doing? How are we moving those electrons?
To the left,
What,
Towards the acceptor, is that right?
yes.
I heard another voice too. What were you getting ready to say?
oh, I was gonna say you would take the lone pair from the carbon and make a pi bond.
Good, yes. And then boom, like that, is that right?
Yes.
And so now my next resonance form will look like this, right? Where you have oxygen now with 3 lone pairs and negative. And then this is CH. And then this is CH. And then this is CH. CH2. Are y'all following? Right? Now, what you'll notice in this molecule is that you have multiple opportunities for resonance. That I tried to develop like a little tool to help you figure out like how many resonance forms are possible. And so it's an approximation. If you have a donor, like the one you have on the end, the CH2, and 2 acceptors, if you add them up, you have 3 things. And so you're going to have, this is approximate now because it doesn't apply to cations. I got to figure out like how to make that apply, but it doesn't apply to cations. It's an approximation. So you'll have 3 resonance forms. Are y'all seeing that? So I started out here, and then I have a form here and a form here. And that's because the one question that always comes up is, how do I know when to stop? Or when should I stop? If you have a donor, you can add up the donors and acceptors, and it'll give you an approximate number of forms that you should have, right? So I have 1 donor, I have 2 acceptors, I have 2 pi bonds present, so those both can act as acceptors. So I have 3 things total. Then I'm as an approximation, I should get at minimum 3 resonance forms, starting with the first, what I started with, and then I have another resonance form, and then I have 1 after that. Everything from here is going to be going backwards. Somebody asked that question. Who was that asked a question about that? About going in reverse. I know it was a guy, but I couldn't see who was speaking. All right, we're good on that. Any questions about it?
When you say you see 2 acceptors, are you talking about the C and the H, the 2
No.
pi bond?
No. So that one pi bond right here is an acceptor. You agree with that?
Yes.
But then the CO is also has a pi bond in it, so that can also be an acceptor.
Okay.
Yeah, and it was right in the next resonance form we drew. It was the acceptor. Is that okay? Is that clear?
Yes.
All right. So now let's do another one. Let's do E, because I don't want to run out of time before we touch that. E and C are going to be very similar because they involve, what functional group is this? Anybody?
Alkene.
Oh, ooh, that's good. It does contain alkenes, but do you see how the alkenes are present in like the arrangement? How it's an alkene, and then a single bond, and then an alkene, and then a single bond, how they alternate? Right? We call this particular arrangement an aromatic. I don't remember if that was in the video or not, so it may not. But you're right. Anytime you see a pi bond, a double bond, not a pi bond, because triple bonds have pi bonds too, like that or like that, those are indeed alkenes. Very good. But this particular case, we call it an aromatic because of the arrangement of the alkenes. That arrangement is what we call, and this is not a term that was in any of the videos, but I'm gonna give it to you because y'all smart and y'all can get it. It's called conjugated. How you have a alternating double or pi and sigma bond. So you have a pi bond followed by a sigma, followed by a pi, followed by a sigma, so on and so forth. So this is an example of what we call conjugation. All right, that's very good. Thank you for that answer. All right, let's do E. Let's take it. We're gonna copy it and put it down. Let's see. You know what? We're just gonna draw it. Instead of trying to copy it, I'll just draw it out. That's easier. Let me make sure I put the double bonds how they go. This is E, I think. I got short-term memory issues like Dory. All right, here we go. All right. So now, where's my donor? Where's my acceptor? And this, again, you can see the pattern. It's the pattern is that of an allylic anion. Doesn't always have to be all carbons, but it's in the pattern of an allylic anion. All right. So how would I push the electrons in that pattern? Where's my donor? Where's my acceptor?
Your donor is the oxygen.
Good. Which makes the pi bond by default the acceptor. Am I right? Now I want you to notice something else too when we do this. In this allylic anion system, the carbon right here is going to receive a pair of electrons. So I got to show that as a lone pair. So I'm going to push these here. I'm going to take that pi bond and push it right there onto that carbon. Right. So in the resonance form, it's going to look like this. Sorry. Go back to black. It's going to look like this, right? Boom. How many carbons are in that ring? Anybody?
6.
6. Very good. Excellent. Right. So that's now the carbon there is negative. And what form am I drawing this in? Is that a Lewis? Is it a skeletal? Is it a line structure? Is it a condensed structure? What is it? Okay.
Skeletal.
It's in skeletal form. All right. How many hydrogens on each one of these carbons in the ring? Here, 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 all except for this one. How many hydrogens will be here?
1.
0. Count the bonds to it.
Oh,
You see that?
yeah, I see it.
Yeah. Thanks for that. Thank you for saying I ain't tripping, but if you count the bonds, there cannot be a hydrogen there because it already has 4 bonds. But if you look around the ring, all of these have 1. All right. So for your aromatics, each carbon in that ring is going to have 1 hydrogen on it. All right. And don't be afraid to speak out. If it's right or if it's wrong, if you feel it, say it. That's why we do it now and get corrected here versus doing it on a test and missing points. So it's better to be corrected among family than let the test do it for you. All right. Can we do another resonance form here? Do you see that pattern again? Got a lily anion.
Yeah, you can.
Yeah, you see it. So I can do this. Boom, make that into a pi bond. And again, because it's these three atoms here, right, that terminal carbon is going to get that pair of electrons. So I'm going to share right here on that carbon. Boom, just like that. So then my resonance form is now going to look like this. And I'm going to have a pair of electrons here with a charge, and then that, like that. And how do I know that that carbon has a formal charge of -1? We talked about formal charge already, right? Go ahead. All right, we're going to come back to that, right? But it has a formal charge of -1. I need. All right. Can I do it again? You see the pattern again?
Yes.
So we can do it again here and here, right? Same pattern, same system, allylic anion. I'm just moving those electrons around that ring. What do you think that's doing for the stability, the overall stability of the ring? Is it good or bad? Or great?
Is
Good.
it-
It's great. The more I can take that a negative charge and push it around the ring and share that charge and those electrons with more atoms, the better. All right. All right. So here's the question I always get. It's an age-old question. Like, can I do the next resonance form to take me back to the beginning? And the answer is yes. Right. I have this pattern again, so I can do it again. Boom, boom, like that. And then what I'm going to get, you'll be able to see, you'll be able to tell me in a second what happened. Actually, what I'm going to do is change the color of the alkenes. So you can see the difference. See that? Compare that to what we started with. What happened to the bonds in the ring?
They all shifted one.
It shifted around. That's exactly right. Right? They all shifted. So, but if you stopped here, it would be okay, right? Because if you apply that rule, adding up the donors and the acceptors, you got 3 acceptors and 1 donor. So at minimum, you're going to get 4 forms, right? So you can count the original form and then the other 3, but you can make this last one to show that the electrons in the ring got shifted around. That's fine. All right, we got to stop here because we're over time, but we're going to pick this up on Wednesday, and the exam it'll be posted after class, and it'll probably lead up to resonance, and then on the second exam, that's when we'll get to the intermolecular forces and stuff. I don't want to cram that on you and force feed it, and you not really have time to absorb it. So that'll probably be on the second test, and it may even be a test by itself if we want to stay on schedule. So let's do that. Let's pick this up on Wednesday. Remember, go through your functional groups, learn them, make flashcards out of them, do whatever you got to do on those functional groups to commit them